Hello, today we're learning section 8.1, solving systems by substitution and elimination. Systems of equations. So many problems are best described by more than one equation with more than one variable. When these equations are all linear, we call this a linear system of equations. It's possible to use many variables, but we will only consider systems of two equations with two variables. The solution set is all of the xy pairs that make all of the equations true at the same time. Types of systems of equations. The graph of a linear equation is a straight line, so we can also think of the solution set as every point xy that is on both lines. There are three possibilities. One is that we're most interested in is when the two equations describe lines with different slopes. In this case, the lines will always intersect each other at exactly one point, so we only have one solution to the system of equations. So basically, we're talking about the situation where you have a line here and a line here, and you see that they intersect at some point. The other situations is if you're parallel and you never intersect, or if for some reason you graph the same line twice and then they'd intersect at every point. But this one solution is the nicest part, or the nicest situation for us right now today. To solve the system's equations, illustrate your solution graphically. So here we have y equals 2x and y equals x plus 1. So we can graph this. We can solve it first, or we can graph it. Either way is fine. I'm gonna solve it first. So if y equals 2x and y equals x plus 1, that means 2x must equal x plus 1. So that means if I move the x to the other side, x must equal 1, because I subtracted x from both sides. And so that means if x equals 1, well, y is equal to 2 times 1, so that means y equals 2. So I should have an intersection of the point 1, 2. It should be a solution. One solution. You can also call it consistent. So let's graph those lines. So this line right here, it's going to have a 0, 0 y-intercept. Plug in 0 for x. If I plug in, let's just say the point we're going to graph, 1, I'll get 2 back out. So I'm going to graph those points. So I'm going to graph 0, I'm going to go over 1, and up 2. So this first line right here. We graph this point right here, and this point right here. I'm going to get the following line. Next one, I can graph, it's going to have a y-intercept of 1. And it's going to have also, if we plug in 1 for x, we're going to get 2 back out for y. So I'm going to plot the point 0, 1, and then this point as well. They look exactly like the same color on the screen. I just realized that. That probably didn't help any. Nope. But yeah, so, oops, I don't want an X there. I just want to say a dot. Because that's the red line. It's supposed to be the light purple line. Can't really tell. But nevertheless, you can see these two lines both have positive slope. One has 2, one has 1. They intersect. They have different slopes, so they should intersect somewhere. And here they intersect both at the point 1, 2. And we graph some other points, they would still intersect at that point. Two types of systems. There are two other types of systems of equations. Both occur when the equations describe lines with the same slope. A dependent system is when two equations describe the same line. So that was there. You did something silly and you didn't realize you were graphing the same line twice. And an inconsistent system is when two equations describe parallel lines. So that's when you have the same slope, but they share no point. They have different y-intercepts. And there are no solutions. Any system with at least one solution is called consistent. So back here, we would call this, like I wrote before, we would call this, I think in Hawks, you would check one solution, consistent. So example, this system has no solutions. There's no way for 2x to equal 2x plus 1. The system is inconsistent. And you'll find that out because when you try to plug in, you say, oh, y is equal to 2x. If you try to solve it, you'll say 2x equals 2x plus 1 because you're setting the equations equal there. Your x's cancel and you get something like 0 equals 1. And then that never happens. So that's inconsistent, no solution. So you'd say empty set, no solution, and you'd say inconsistent. Every pair, in this case, x times 2x, x comma 2x is a solution to this equation. It's dependent because once you pick one variable, the other variable is determined. You can see this once again. If you were to go solve something like this, say y equals 2x, you'd say 2 times 2x equals 4x, because I'm plugging this 2x in for y. And you'd have 4x equals 4x, and then if you cancel the x on both sides, you get something like 0 equals 0. Well, that's always true. If it's always true, it's going to be all real numbers. Oops. I should say not all real numbers. I should just say infinite number solution. Infinitely. I say infinitely many solutions. And they're in the form. And usually you solve for x and say x, once I pick x, my y is determined, my y has to be 2x. And you can just do this and solve this. Like if you ever get a dependent system, they're the same equations, they're usually multiples of each other. And if you want to put it in the form of the solution, basically you're going to say x is equal to x and y is going to be equal, you just put it in slope-intercept form, so you have y equals something, and you just put this part of the line, y equals whatever it equals right here when you put it in slope-intercept form. I don't think there are many dependent ones in the homework, but they do happen on occasions. Focus. All right. Solving by substitution. Substitution is one way to solve a system of equations. To solve a system of equations by substitution, we solve one equation for one variable, substitute this expression to the other equation. This equation will now be a single equation in a single unknown. Number 3, we solve for the equation from step 2. We learned how to solve linear equations way back in 2.1, 2.2. Number 4, substitute the result back into the solved equation from step 1. Alright, so here, so whenever you're solving by substitution, basically you want to find a variable that either has 1 as a coefficient, and you know, if y has 1 coefficient, we typically solve y in terms of x, so a lot of people do that. So if it's possible, if you see that leading coefficient in front of y in any one of your problems, or any one of your variable, or your equations, I would just pick that right off the bat. That's usually easiest. Now, if you don't have a single, if you don't have a 1 leading your coefficient, you can make that happen by dividing by whatever number you have in terms of your, you know, if let's say you want to try this to be 1, you divide everything by 3. But you always avoid division to get a leading coefficient of 1 if it's going to give you fractions. Because once you start getting fractions, it's fractions all the way down. You're going to get fractions. Your answers may still be integers, but all your calculations are going to involve a lot of fractions, which usually, you know, when you're doing linear equations, you try to avoid as much as possible because there's really no need to be for fractions for us right now. So I'm going to rewrite this first equation as y equals 9 minus x. So now I'm going to take this 9 minus x, I'm going to plug that in for y right here. So now my new second equation becomes 3x plus 4 times 9 minus x equals 30. So that becomes 3x plus, and then you're going to have 4 times 9, which is going to be 36, minus 4x, because it should be that 4, equals 30. So I'm going to combine the negative 4 and this 3x and negative 4x. I'm going to get negative x, and then I'm going to minus 36 from both sides because I want my constants on one side. I'm going to get negative 6, so that means x must have been 6. If x is 6, well, I already know what y is because I wrote that equation up here. Y is equal to exactly 9 minus 6. So that means y has to equal positive 3. So in this case, we're going to check one solution. It's consistent. And its solution, and you put it in the form of a point, in this case, 6, comma 3. Remember, this is going to be your x, this is going to be your y, like it normally appear. Next, we have one that's a little bit more involved. Once again, they were real nice, and we try to give you nice examples so you can follow along in the lecture. But sometimes in Hawks, you'll have to do a little bit of manipulation. Like, you know, maybe they would give you all even numbers, and if you divide it by 2, you get a 1 in front of something. We do by elimination. Usually, we don't have a leading coefficient of 1 somewhere. But here we can see that leading coefficient in our first equation right here. So I'm just going to write y is equal to, if the x was 1 and the y was a different number, I'd solve x equals whatever. But here it's y again. So we have y equals, and then I'm going to say negative 2x minus, or sorry, negative 2 minus 2x, because I moved that 2x to the other side. Then I'm going to take this y value, which was negative 2 minus 2x, and I'm going to plug this in for y. So I'm going to get a new second equation of negative 4 minus negative 2 times negative 2 minus 2x, this is my y, equals 5. So now I'm going to get negative 4x minus, and then I'm going to multiply these two, negative 2 times negative 2, get positive 4, and then negative 2 times negative 2 times negative 2x, which will give me plus 4x equals 5. And then you see something interesting happens here. We cancel these x's, and we get a situation where what's happened? We get 4 equals 5. And when 4 equals 5, then that means that never happens, so we'd say no solution, and it's inconsistent. So you check that. So 4 never equals 5. Now, if this happened to be a 4 on this side, we'd have gotten 4 equals 4, and then it's infinitely many solutions, consistent, dependent. But here, if you're manipulating the equations, at some point you get 0 equals a non-zero number, or 7 equals 3, or two numbers that are not equal to each other, all your variables went away, then you're in a situation where you're either no solution or all solutions. In this case, no solution. Well, sorry. When your variables go away, one of two things happen. You get a constant equal to something not itself, and then it's no solution. Or if your variables all go away and you get a constant equal to itself, then it's all solutions. What I meant to say. Describing the same line. If we multiply a linear equation by a constant, the resulting equation describes the same line. For example, we have y equals 3x plus 1 and 2y equals 6x plus 2 describe the same line, because basically we just doubled everything in this second line. If we have a consistent system of two equations and we add them together, the resulting equation will contain any point that is in the solution set of the original system. These facts are the basis for solving the system by elimination. So basically, you know, I'm essentially going to be adding this line to itself, and you'll see that it describes the same solution set. And you'll eliminate both your variables. Solving by elimination. Elimination is another way to solve a system of equations. To solve a system of equations by elimination, we multiply, number one, we multiply one or both of the equations by a constant so that one of the variables will cancel when the equations are added together. Number two, add the equations. This will give a single equations and a single unknown. Number three, we solve the equation from step 2. Number 4, we substitute back into any equations in the original system to find all the variable values back out. So we have this one right here. And so right here, looking at this, if I'm going to eliminate this, I want to eliminate one of the variables at each step, or at this step here. And when you have more variables, 3, 4, or 5 variables, you want to eliminate each one every time you do something. In this case, I want to eliminate, well, x's, I could pick x's, but if I pick the x's to eliminate, I need them to have the same coefficient. If they have the same coefficient, I'd have to multiply this top one by 6 and this bottom one by 5. And that's, I'd rather avoid multiplying two equations when I only multiply one. And the reason why I only need to multiply by the bottom equation, if we look at the y's, not only do they have opposing signs, so I don't have to switch signs when I multiply by a constant, 2 is a factor of 8. So all I have to do is multiply the bottom equation by 4 to get 8y in both places. And you make sure they have the opposite sign. So I'm going to say the bottom equation, I'm going to multiply it by 4. And so I'm going to get a new system where I have 5x minus 8. Well, not a new system, a modified system. 5x minus 8y equals negative 47. And now I'm going to have negative 4 times negative 6 is negative 24. And then I'm going to have 4 times 2y, which gives me positive 8y. Now I have the same coefficient with opposite signs. And then I'm going to say 4 times 26. Well, 4 times 5 is 100. Or sorry, 4 times 25 is 100. So one more would be 104. All right, so now I can add these together. And remember, you want to eliminate one variable when you add these together. If you don't eliminate any variable, then you pick the wrong thing to multiply. Or if you eliminate both variables, you're in that situation where you have all solutions or no solutions, dependent or inconsistent system of equations. So looking at this, what we're going to do is we add these two together. And so I'm going to get negative 19x, 5x minus 24x. And then I'm going to get 0y because I'm going to have negative 8y plus 8y. And that's going to give me plus 0y. You don't have to write the 0y there. Then we're going to have negative 47. And then I'm going to add that to 104. So put that in the calculator real quick. Negative 47 plus 104. We get 57. Focus. Nope. Did for a second. And so now we have 57. And then we divide. So now we're going to have negative 19x equals 57. So I'm going to divide both sides by negative 19. So now I'm going to have x equals 57 over negative 19. And so when I divide 57 by negative 19, I get negative 3 back out. So now I know what x is. So I can pick any one of these equations. Pick the original equations, because chances are you multiplied these equations by some constant, made it bigger. The bigger the numbers, more likely you are to make a mistake. So go back to the original equations, especially it'll help check to make sure you didn't make a mistake. And then we plug in negative 3 for x, so we'll have 5. You can pick either equation. I just happen to pick the first one. 5 minus 3 plus 8y equals negative 47 gives me negative 15 plus 8y has to equal negative 47. So that means if I add 15 to both sides, I'm going to get 8y equals negative 47 plus 15. So let me do that real quick off to the side. It's going to be negative 32. Then I'm going to divide both by 8. And I'm going to get my y value is now, thank you. Y is equal to negative 32 over 8, which is going to be negative 4. I'm almost positive. And so now we're going to get that situation where we say it's one solution. One solution is consistent. And its value is going to be negative 3, negative 4. And if you want to check this, you can plug them into both equations to make sure these points make sense. I could plug it into the other equation if you just want to check that real quick. You could say negative 6 times negative 3 plus 2 times negative 4. And that should give me 26 back out. Let's see if that works. That's going to give me positive 18 plus, oops, not negative 4. I've misplaced something somewhere. See, this is why it was good to double check. Because right here, you all might have noticed 3 or 4 minutes ago, this is negative 8y. I was thinking positive 8y because I got positive 8y over here. I wasn't looking in the right place. This is supposed to be a minus. This is a minus. This is a minus, minus, minus. This becomes a positive 4. This is supposed to be positive 4. Once again, always good to check your answers. And then we'll say that this is supposed to be positive 4. So now I'd get 8. 18 plus 8 is 26. So once again, always good to check your answers. In this case, one solution, negative 3, positive 4 was your answer there. So yeah, be careful about that. It's easy to make a mistake because once you've made one math error, you'll follow it all the way down. And usually the only thing that tells you did something horribly wrong is you'll get horrible fractions back out. Here, I got a reasonable answer. I just dropped a sign. And if I didn't check it in my second equation, I would have never noticed it. Because if I checked it back in the original equation and I copied my same mistake, yeah. Really easy to check your answers there. Alright, so now we want to solve this system of equations. So here we want to eliminate one variable, and we already see the x's can be eliminated pretty quickly. So if I just draw a line right here, they have opposite signs, same coefficient, and I'll get 0x, but then I notice I also get 0y, and that equals 0. So that means we're going to have infinitely many solutions. And infinitely many solutions, so it's dependent. Dependent. It's dependent, and I lost my train of thought because I can't spell. It's dependent, and we're going to say it has infinitely many solutions. It's dependent. It's also consistent because it has at least one solution. But usually when you say something is dependent, it implies that it's consistent for us. And so what is the form of the solution? The form of the solution is going to be basically, if we solve one of these equations for y, I'm going to pick the second equation right here because it's easier. I'm going to have y equals, and if I move that 2x to the other side, 2x plus 12. So everybody see this? I got y equals 2x plus 12. All I did was move the 2x to the other side in the second equation. And so now we have this, and we say they're going to be the form where x can be any real number, and then y would be what? Y is equal to 2x plus 12. And that would be your solution. X, because once you pick your x, your y is predetermined. That's why it's dependent. X, or y in this case, depends on x. Once we pick x, we'll automatically get an infinite number of solutions back out because we have infinite number of choices. You know, x is any real number. Once we pick that, we've determined our y, which is 2x plus 12. Alright, so here we have a application problem. And so it says, in exercise 6, it says how many ounces of a 12% alcohol solution and a 30% alcohol solution must be combined to obtain 60 ounces of an 18% solution. So what it's asking here is that I'm going to have two unknown amounts, right? I'm going to have x plus y, two different solutions, going to have to give me 60 ounces back out right off the bat. And of that, let's say that my 12% solution is my x solution, or x alcohol solution. And then my 30% alcohol solution is going to be equal to y. That's going to be my y. So I'm going to say over here for my 12%, well, I have x ounces of them, so I'm going to say 0.12. And that's going to be times x plus 0.30y, because this is my x solution, my y solution, 12%. And then that total, x plus y, we said had to be, what do we want back out? We want an 18% alcohol solution. But of those, if this was 12% alcohol and that's 0.3% alcohol, we want 0.18. But how many total ounces of alcohol do we have? Well, we have 60. So we have to have 18 times 60 for this one right here to determine the total amount of alcohol. Because every time we add an ounce of each, we're trying to add, well, we're going to add overall to the overall amount of alcohol in the solution. And so for the total solution, it's going to have 60 ounces. So 0.18, 18% of that 60 ounces is going to be in there. So now that I have this figured out, I'm just going to rewrite my equations as x plus y equals 60. And then I'm going to have 0.2x 0.12x plus 0.30y, and that's going to equal, and we're going to say 60 times 0.18, and that's going to give us 10.8 back out. Now, there's a couple ways we can work this. We can do elimination, but we do elimination, we're going to have to multiply by 100 to get rid of all these decimals, right? And that's easy to do. Your numbers are going to get pretty big, though, because now you're talking about if you multiply this 10 by 100, you're going to get, 1,000 back out? And so your numbers get really big. But we have x and y in the first equation. X plus y has to equal 60. The y, if we solve for y in this one, so we take this over here and we say y equals 60 minus x. Well, if I have y equals 60 minus x, I can plug that back in, and we'll just solve by substitution instead of elimination. So elimination would have given us, we could have done it with elimination. It would have just been, our numbers would get really big. And if you're okay with big numbers and doing those on a calculator, that's fine. You just have to multiply this by 100. But not only that, you'd have to multiply it by something that would cancel with an extra y. So you'd eventually multiply probably the top one by 12, the bottom one by 100 to get rid of all your decimals. Yeah, to be wary of those fractions, because like I said, once you start getting fractions and decimals, there's fractions and decimals all over the place. Here I'm not changing anything. I'm going to keep the decimals here because they're nice terminating decimals, and I'm going to have so now I'm going to have 12x plus 0.30, and then that used to be y, now changed to 60 minus x, and that's going to equal 10.8. So I'm going to get 0.12x plus 0.3, and I can drop that 0. I don't need to say 0.30. And I'm going to say 0.3 times 60 minus 0.3 times x equals 10.8. And so I'm going to have 0.12x minus 0.3x, and then 30 times 60, 3.3 times 60 is going to be 18. It's going to be 10.8 over here still. And then when I take negative 0.3 and I add 0.12 to it, my coefficient on my x becomes negative 0.18x plus 18 equals 10.8. So now I'm going to move the 18 to the other side. I'm going to move that 18 to the other side. I'm going to get negative 0.18x equals 10.8 minus 18. So I'm going to get negative 0.18x equals, and then that's going to give me 10.8, subtract 18 from it, and I'm going to get negative 7.2. And then I'm going to divide both sides by negative 0.18, negative 0.18, and so that's going to give me x equals 40. And then so if x equals 40, well, 40 plus y has to equal 60, so y must have been 20. So my answer is one solution. It's consistent. And it's going to be 40 for x and 20 for y. And that's your answer. One thing I want to mention real quick is non-negative constraints. Here, sometimes you have constraints in your problem and you don't realize they're in your problem, and you can have weird things happen. Like, let's say something that may have a solution, but not be a solution you can use. If for something you had to mix two solutions and you needed a negative ounces of one, because ounces are understood, like if you have a solution, you can't have a negative amount of volume. Negative volume doesn't make any sense, just like negative area or negative distance. So with that in mind, you might say, well, my solution came out to a number, but it was negative, so that's not useful. So we have these non-negative constraints. Y has to be greater than 0, or equal to 0 or greater, and x has to be equal or greater than 0. Because if you don't have that, if you don't understand that, when you start the problem, that's, we don't encounter problems like this in this section where, you will get a solution, but that solution won't be a valid solution. But later on, other mathematics, you may encounter that where you get a solution, but you have constraints on your variable that says that's not a valid solution. So be aware of that. But yeah, that's it for today. You all have a great one.